Hello everyone, my name is Siddharth Agarwal and I'm a Master of Science student at the University of Melbourne, Australia. And I'm very happy to be virtually here with you today to present our work, a reinforcement learning approach to reduce the function cold start frequencies in a serverless compute setting. I'd like to start with a brief introduction of what serverless is, specifically its function as a service offering. It can be understood as a different execution model of cloud computing wherein the burden of resource provisioning, configuring, management, and patching lies with the cloud service provider, and the user or the developer solely focuses on the application development. Serverless in no way means the absence of servers. Instead, it highlights the shift of the responsibilities from the user or developer towards the cloud service provider. It is based on a pay-per-use pricing model where the users only pay for the actually consumed resources. Function as a service is an event-driven architecture which has high elasticity and resource utilization. In function as a service model, we simply write the code and plug this application code in the form of bounded time stateless functions, which are reachable through an endpoint, which gives the result on demand by spinning up new function instances for individual requests. So compared with the traditional cloud computing execution models, function as a service provides an abstraction of servers with a reduced responsibility of resources, aiding to the increased development agility with a highly scalable and available function model. A broad range of applications like stream processing, Internet of Things applications, edge computing, chatbots, APIs, mobile backends, and even some machine learning inference tasks makes use of the serverless platforms. So if we focus on different deployment models of cloud computing, then we can clearly see that the serverless stack clearly differentiates itself from the other execution models and offers the ease to focus on the development agility while hiding the underlying details. With the initial introduction of serverless with AWS Lambda by Amazon in 2014, there are multiple industry-grade serverless options available like Azure Functions, Google Cloud Functions, IBM Cloud Functions, and a few open source frameworks like Apache, OpenWhisk, and Kubeless. A simple application in a function as a service setting can be thought of having a function as an endpoint of the service that interacts with the backend or performs the desired action and returns a result without us having to worry about the underlying resources and its availability. With the abstraction of infrastructure, there's a lot of ease as a developer or user since we only pay for what we use and the application is highly available and scalable. But the things get a bit difficult on the other side of the picture, that is the cloud service provider who is actually accountable for all these abstractions. The cloud service provider is responsible for providing the services like resource management, patching OS, providing secure and isolated function environment, and an impression of unlimited scaling of the function, optimize the resource utilization, etc. But as a computing platform, serverless suffers from some inherent challenges like function cold starts, resource limits, vendor lock-in, cross-platform executions, security and isolation of business logics, etc. These could be characterized to the aforementioned areas of concern, which also poses a great opportunity for further innovations and make the platform available to other market sections as well as the other application domains. In the current work, we are exploring the challenge of function cold starts. Since as a user, we are only concerned with the response time of our applications, how quickly we can get the result, and we're not concerned about what goes behind the curtain. But as a cloud service provider who actually services the user as quickly as possible, with application functions spinning up on demand and returning the desired responses. This spinning up of new function on demand is the preparation of new instances and typically takes some time in the order of few milliseconds or seconds. The preparation time for this function instance is known as the cold start and introduces some delay in the response of the application. These cold starts have few underlying factors like runtime environment used, function dependencies, networking requirements of the instance, workload concurrency, etc., which affect the performance of the business logic, which is wrapped as a function. So what actually contributes to the cold starts? What are the stages that a function goes through before acting to the incoming requests? So in this section, we define the function cold starts, function warm starts, and how the different factors affect the function as a service performance and how do they compare against each other. So let's consider an example where a request is made to the function for the first time. The platform checks for the available function instances in the memory to service the request. If there are no instances ready, a new function instance is initialized that includes downloading of the function code, allocation of the required resources, identifying environment setup and dependencies before the function could actually carry out the request. This entire setup time is known as the cold starts. But when a function instance is already present to serve the incoming request in the memory, the process of initialization is altogether skipped and the function handler is directly invoked to perform the request. Therefore, there is no delay before the actual execution of the request, and this time is known as the function warm start. Therefore, if we carefully observe, we can infer that the cold start is potentially an important challenge that the platform needs to deal with. Or particularly if we say that the cloud service provider needs to investigate to improve its platform's efficiency. A default approach that industry-leading platforms applies to keep a warm queue of functions, that is, keeping idle functions running in the memory to anticipate the future workload. But this comes at the cost of resources and introduces a trade-off between the resources and the cold start of the functions. The mitigation techniques which are explored by community can be categorized in two categories, either reducing the cold start time itself or reducing the frequency or the number of cold starts that happen on the platform while serving the incoming workloads. Consider a few solutions like continuously interacting with the function endpoint to keep the instances in the memory or in the ready queue, pool-based approach of keeping empty containers or function dependencies already created up in the queue. But these address the cold start problems but propose a non-intelligent solution that keeps the resources bound. Therefore, we explored an approach where a smart reinforcement learning agent tries to reduce the frequency of cold starts based upon the invocation patterns of a particular application. This way, the agent can learn to optimally anticipate the number of function instances required to serve the next incoming batch of requests based upon the learned patterns, and therefore helps us to reduce the frequency of cold starts by preparing right number of function instances in advance and thereby also reducing the failed number of requests by the functions. Since our agent is focused on analyzing the invocation patterns and predicting the optimal number of function instances required to serve the respective workload, out of the two categories discussed before, this work can be categorized under the second one, which is the reducing of frequency of cold starts on the function as a service or the serverless platforms. Let's take a look at what reinforcement learning is, since our agent is based upon that. So reinforcement learning is a distinguished area of machine learning which involves training of a model to make a sequence of decisions. It encompasses the concept of an environment wherein an agent interacts with it via actions, transitions between states, and observes rewards associated with these transitions. Therefore, the main components of the reinforcement learning process can be highlighted as the environment itself, the states, agents, the actions of the agents, and the rewards that the agent observes. In the present work, we apply the very basic approach of Q-learning for training a model that allows our agent to take actions, actions being increasing or decreasing the number of function instances, and store the corresponding rewards of these transitions into a Q table. This Q table in turn serves as a lookup table to decide on to the next best action from the current state, transitioning into the next one. So the Q tables are updated as per the Bellman equations. which consider the agent learning rate and a concept of discounted future rewards that an agent might expect to receive in the near future. The table is prepared for every state action pair, and the agent decides the next best action based upon the maximum value against the current state in the queue table. Now let's understand the overall system architecture that we've used for this particular experiment. So we took advantage of the easily deployable open source serverless platform, which is Kubeless here. It makes use of the underlying Kubernetes resource structure since it's a Kubernetes native framework and provides a function as a service platform over it. The entire setup was modeled on 4 nodes Kubernetes cluster with the reinforcement learning agent deployed on the master node. The agent directly interacts with the kubeless and Kubernetes CLI, which is the command line interface, and performs the action of increasing or decreasing the number of instances to transition between different environment states while receiving rewards for the respective actions. To mimic the serverless workload and allow the platform to observe some cold starts, a compute intensive workload, that is the Fibonacci calculation of number 38, has been chosen with a variety of invocation patterns, which has been examined for a period of 240 minutes, which forms a single epoch of the training, with a time interval of 5 minutes to the take the observed delayed reward from the environment. With all this setup, the kubeless and the Kubernetes platform with its resources, this entire thing forms the environment for our agent, and the and we model the environment states as the combination of CPU utilization of the function instances along with the number of pods currently available in the environment. The agent takes the action of increasing or decreasing the function instances by a selected amount following the epsilon greedy policy to explore and exploit the information gained by receiving different delayed rewards. The agent scrapes the required matrix using the command line interface and processes the entire information to calculate the rewards as well as the next state for our agent. So the agent learning process goes like this. The agent records the current state, which is a combination of function instances and the CPU utilization, looks up the queue table for maximum value against the current state, and accordingly scales up or down the number of instances with a certain number. The workload, on the other hand, is generated as a number of requests for a period of 5 minutes, and the selected action by the agent tries to serve them. After the period of 5 minutes, the agent observes the CPU utilization with the number of current instances and scrapes the relevant matrix to calculate the failed number of requests as well, since it is also used for our rewards. Based upon these values, an immediate reward is awarded to the agent for the particular state action pair, which is further updated in the queue table using the Bellman equations, hence leading to the learning of our agent. So we've compared our agent with the default horizontal pod auto scaling policy by the Kubernetes on which the kubeless works. Since horizontal pod auto scaling policy is implemented as a control loop, it analyzes the CPU utilization of the function pods available, and based on a particular threshold which is already configured or by default, it scales up or down the function instances. So by default, the platform keeps the allocated resources for up to a period of 5 minutes so as to prevent the resources from thrashing. Therefore, this particular thing presents as a perfect baseline model, and thus also explains our decision of keeping the observation time interval of 5 minutes. If we compare our results between the default horizontal pod auto scaling policy and our agent, we can see in the figure 1 that there are a lot of spikes, or we could say there are a lot of failed requests for the default horizontal pod auto scaling policy for a period of 240 minutes with a time interval of 5 minutes. But if you look at the figure 2, which is the fourth iteration of our Q-learning agent, we can see that these spikes have been reduced by a learning agent, or we could say that these spikes represent the failed number of requests, and the agent is capable of reducing these failed number of requests over the iterations. So in comparison to the baseline approach of the default auto scaling, our approach shows the practical applicability of the reinforcement learning algorithm to reduce these cold start occurrences for a specific function workload and closes on the difference between the successfully served requests within the few iterations. So to conclude, we saw that with application response time being one of the most important factors for an end user, the serverless or the function as a service platform introduces some overheads of the cold starts. While various approaches have been proposed to reduce these challenges, these are non-intelligent solutions since these are not based on the invocation patterns, or these are not learning the invocation patterns, and also these bound the resources with themselves. Hence, we have presented an evidence of using a reinforcement learning technique and proposed an agent that learns from the unknown invocation patterns to ascertain the optimal number of function instances to reduce the cold start frequencies of the function. By comparing the result of our approach with the existing auto-scaling technique, we successfully observed that within a few or limited number of iterations, the agent was able to show moderate results by serving approximately 50.1% of the requests. Hence, our approach shows a practical applicability of the reinforcement learning algorithms for reducing these cold start frequencies for a specific function workload, and it closes on the difference between the successfully served requests within a few limited iterations. I thank you for your attention, and I'd like to encourage you all to go and read our paper for further details and information which can be used for further studies. Thank you.